Okay, in section 7.2, we're going to be measuring the quality of a survey. We're going to use a simulation to develop an understanding of the behavior of estimators. Or an estimator, oops, got to turn the pen on. Estimators are things like p-hat. All right, so we're going to consider the 8 students in the classroom to be the population. So we've got a very small population. Got this population size is 8. And the students in this classroom consider themselves to be either cat people or dog people. Following lists the students and their ID numbers, and to keep things simple, the students are not listed by name, but by their cat or dog status. So for instance, C is for cat status, and D is for the dog status. All right, so what is the proportion of cat people in this population? So we've got a parameter, and if we look, we've got 2 out of the 8 are cat people, which is 25% of the population. And what symbol do we use to represent this parameter? We got our symbol is P. So we're going to be using P to represent a population proportion. All right, number 2, we're now going to take a random sample of size 4 from this population. Following is a copy of a portion of the random number table from the back of your textbooks. And I randomly selected the first block in line 6 to start. So this first column, notice, is just line numbers, so it helps you communicate with somebody else if you're working together. So I started in line 6, which is right there. So here's the set of numbers that I'm going to be looking at. So I'm going to close my eyes, I put my finger down, I happen to land right there. All right, so reading from the left, I'm going to select the following ID numbers and students. And I'm going to skip ID number 9 since there's no student with this ID number. So I've got 8, 7, skip the 9, 6, and 4. So here's those ID numbers right from that line in the random number table. All right, so we now look back up to our population, and we can see that ID number 8 is a dog person, ID number 7 is a dog person, 6, and 4. We've got all dog people, so that's how we filled in this bottom row of the table. All right, so what proportion of cat people in this sample? We have 0 out of the 4, or 0%. And what symbol do we use to represent the statistic? This is a p-hat. So our p-hat in this particular sample is 0%. Number 3, let's take another random sample of size 4 from this population. I randomly selected the third block in line 1 to start. So again, when I close my eyes, I put my finger down, my finger landed right here on that 1. So I'm going to again read from the left, and I'm going to select the following ID numbers and students. And if I look, I'm going to have to skip ID number 9 and 0 because I have no students that correspond to that. All right, so reading those ID numbers, I have 1, 3, 5. Oh, I have another number I have to skip. And 6. So 1, 3, 5, and 6. So that is this top row right there. And if we flip back a page, which I'll let you do to verify, we're going to find that ID number 1 is the only ID number in this sample that goes with a cat person. So the proportion of cat people in this sample is 1 out of 4, or 25%. And since this is another sample, our symbol is p-hat. Okay, let's do one more. So number 4, let's take one more random sample of size 4 from this population, and this is our last one. I randomly selected the third digit in the third block in line 3 to start. So when I put my finger down, I was in the third block, so 1, 2, 3, and I saw the third digit to start. All right, and I think I can take 2, 5, 1, and 8. I don't have to skip anything this time. That gives me my ID numbers in this table. And again, thinking back, just ID numbers 1 and 2 were cat people, so 5 and 8 are dog people. So the proportion of cat people in my sample is 2 out of 4, or 50%. And again, that's a p-hat, because that is a result of a sample, or it's a value that summarizes our sample. Okay, so let's take a look at our results so far. So we did 3 samples, so 3 repetitions. Each time we took a sample, keep in mind that our population hadn't changed. Our population parameter was always 25% of the population preferred cats or considered themselves cat people. And our sample statistics, though, on the other hand, varied. So the first time we took a sample, we had 0% cat people. Second time, we had 25% cat people. And the third and final time, we had 50%, or half of the people in the group said they were cat people. So 0% of 4 is where the number of cat people comes from. If we did 25% of 4, we'd get 1 person, and 50% of 4 gives us the 2 people in the last column. All right, so some observations. Your population proportion P never changes. And if you look at that column, the population never changed. Every time we took a sample, it was from the same population. And the sample proportion P hat did change. That one changed from sample to sample. And can is an important piece because if we took another sample, we'd get one of these 3 numbers potentially. It's just that it could change or can change from sample to sample. In other words, it varies from sample to sample. This is because P hat depends on a random sample. So keep in mind, statistics vary from sample to sample. All right, number 6. In this simulation, we collected 3 samples, and we counted the number of cat people in each sample. So we're going to complete the following approximated probability distribution from our class. And it's approximated because it came from a simulation and was based on sample results. All right, so 0 cat people happened 1 out of the 3 times we took a sample. 1 cat person was 1/3 of the time, and 2 cat people was 1/3 of the time. So each of these is about 33%. So here's our estimated probabilities. So if we draw the probability distribution on the right, so notice our vertical axis says probability, we're going to have a bar above 0, or a line above 0 that goes to 0.33, one above the 1, same height, and one at 2, same height. This is the number of cat people. All right, so number 7, we can also consider P hat to be our outcome of interest. Because P hat is random, it also has a probability distribution, which we're going to call a sampling distribution. So sampling means we've done repeated samples, or it shows you how a bunch of samples are distributed. All right, so it's called a sampling distribution because P hat is a statistic from a sample and is used to estimate a population parameter. So let's create the approximated sampling distribution based on the results of our class simulation. So again, it's approximated because it comes from a simulation. All right, so for our sampling distribution, from the sample results we had 0% cat people 1/3 of the time. We had 25% cat people 1/3 of the time. And half of our sample, or 50% of our sample, were cat people. So notice the primary difference between what we just drew and what we had up here is the scale. The first one we drew talked about number of cat people. So this was talking about discrete variables. And down here we're talking about sample proportions. So these are P hats on this axis. So you can just think about this axis as having been rescaled. So for instance, 0%. 0% of 4 is 0 cat people. 25% of 4 is 1. And 50% of 4 is 2. So again, we're just rescaling this axis. Okay, so what does the exact sampling distribution look like? So in theory, what would it be? Not just based on a simulation. So keep in mind there are only 3 possible outcomes, or 3 possible values of P hat in the sampling distribution. You can get 0 cat people out of the 4 students in your sample. 1 of the 4 students could be a cat person, or 2 of the 4 students could be cat people. So just a reminder, there were only 2 cat people in the population, which is why we're only seeing these 3 possible outcomes. All right, so the probability of each of these outcomes can be determined by looking at the sample space for this random experiment. Turns out that there are only 70 possible outcomes, or 70 possible samples of size 4, and we're not going to list them right now. In fact, rather than listing these outcomes here, we're just going to focus on how often each outcome occurs. All right, so the probability of obtaining each p hat is shown in the following probability table and in the following sampling distribution for p hat. So notice these are not approximated distributions anymore. So not approximated. These are exact or theoretical, and they didn't come from a sampling distribution. So notice here in the probability column, is telling you how many outcomes out of the 70 had each potential outcome. So for instance, there were 15 samples out of 70 total samples possible, which is about 21% of the samples had 0% cat people, which also means that 0 out of the 4 people were cat people. Okay, in graph form, vertical axis is labeled as probability. So notice that probability we just looked at, it's right here. 0% cat people has a probability of about 0.21. Getting 25% of your sample saying they're cat people, a little under 60%. And half of your sample, or 50%, are cat people, also about 21%. All right, so a few observations. The mean of this distribution is p equal to 25%. So notice that's right in the middle of that distribution. It's the balance point. Also keep in mind that our estimator p hat isn't always equal to p. Right? You could get a bunch of different values. You can get p equal to 0%, 25%, and 50%. And keep in mind that statistics that come from random samples are also therefore random. This means that we cannot know what estimate our sample will produce until we analyze the sample. Even though our estimator p hat isn't always equal to p, we are never more than 25 percentage points away from p. In fact, the standard deviation for this distribution is 16.4%. That's an important thing to keep in mind. And we may not get a sample result exactly equal to 25%, but they're never more than 25 percentage points away from that. And so our last question here, how does our approximated sampling distribution compare to the exact sampling distribution for this experiment? And I would say that they're similar. In fact, not the same, not identical. And more specifically, they're both symmetric. They both have a mean of 25%. And the exact sampling distribution, though, is mound shaped, so different shapes. Well, they're both symmetric, they're different shapes. One is unimodal, so the exact sampling distribution is symmetric and unimodal. And the approximate one is symmetric, but not unimodal. In fact, it was uniform. Right. In order to see these two closer together, one resemble the other, we would need more samples, more repetitions, so that the, again, approximated sampling distribution would get closer to the exact sampling distribution. All right, number 9, when measuring the quality of a survey, we'll be interested in evaluating the estimation or sampling method used, not in a single estimate from a single sample. So there's still 2 questions that we need to address. Question 1, are the results from a particular sampling method accurate? So in other words, are the estimates centered at p? This can be measured in terms of the bias. A biased method will produce results that are not centered at p. So what does a sampling distribution look like when the results come from an unbiased sampling method versus a biased sampling method? So let's put unbiased here, and we'll put biased over on the right. All right, so if it's unbiased, that means the center should be at p. And let's assume for now, put an assume here, that we're still dealing with the previous population and that P is 25%. So if an unbiased sampling method, or unbiased sampling distribution, unbiased sampling method, means our center should be right at P. So our distribution might look something like this. Okay, so notice that our center, again, is right at P equal to 25%. In fact, if we calculate the bias, we would say that the bias is 0 because the center is the same, or the difference between the center and where we expect the center to be is 0. All right, if your distribution is biased, on the other hand, you might have a distribution that looks like this. And in this case, we tended to underrepresent or underestimate the proportion of cat people in our sample. So notice here, our center is not at P. In fact, our bias, we can measure that. You do 0.05, which is where, I would say our center is more like 0.10, minus the center we expect, gives us an answer about negative 0.15. And the important thing is here is this is not 0. Because again, we expect the center to be right there. So we have a difference of about 15 percentage points. Okay, question number 2. Are the results from a particular sampling method precise? In other words, are all of the estimates similar in size? So what does a sampling distribution look like when the results are precise and not precise? So let's once again assume that P is 25%, just to make things easier. And let's look at bias or precise on the left, what it would look like, and not precise we'll look at on the right. All right, so precise. We're expecting 25%. Maybe we get all these results like this. And they're tightly clustered right around 25%. That tells us that we have a lot of precision. And notice that means that we have less variability here in our results. So precision is another word for variability. Over here on the right, if it's not precise, we might see a distribution looks like this. So notice here we've got a lot more spread. In fact, we could even imagine this continuing on to the right. Very unprecise or imprecise results. So this is not precise, which means there's more variability. A lot more spread in our results. All right, so together bias and standard deviation are used to quantify the uncertainty in our inferences. So let's return to our approximated sampling distribution in number 7. So again, you may want to press pause, flip back to that, take a quick look at it. So the question is, do you think our sampling method was accurate or unbiased? If you check the center, you'll find that our answer is yes. The center was at 25%, which was P. And do you think our sampling method was precise? This one's a little harder to answer, so let's say that it was somewhat precise. Our standard deviation was about 16%. Okay, so no P hat was more than 25 percentage points from P. Since this is our first example, we don't know if that's pretty big or pretty small. And we'll have a better idea of that as we go. And one last question they might want to consider is, how can you increase the precision of the sampling method? So what can bring you from a distribution that looks more like this one to this one? And what we're going to find is that has something to do with our sample size. All right, so key features of our sampling distribution. Keep in mind it's your probability distribution for your statistic. And our statistic in this case that we've considered so far is P hat, or sample proportion. It also shows all of the possible values of the statistic on your horizontal axes. If you look at these previous distributions we created, I'll just put a rough copy of one up here. You'll remember that P hat was on the horizontal axes. So that's our statistic. All right, third, it gives us the probability of each possible statistic. So if you look more closely at those graphs we considered, your vertical axes gave you the probability. So the heights of those bars, where they were relative to your vertical axes, gave you probability. And so that means it tells you how often you can expect to see particular values of your estimator. And the fourth bullet, it gives you important characteristics of the estimator, such as bias and precision. So remember, bias is measured using the center of the sampling distribution. It's the distance between the center and the population value p, and your hope is that this center value is the same or equal to p. Precision is reflected in the spread of the sampling distribution and is measured by the standard deviation of the sampling distribution. Standard deviation of a sampling distribution is called the standard error. Some textbooks still call it standard deviation, but our text is going to switch to standard error. This is very specific. Again, it talks about the spread in your sampling distribution. So it measures how much your estimator typically varies from sample to sample, or how far estimators typically are from the mean p. So the smaller the standard error, the more precise the estimator. And because it can be called either standard error or standard deviation, its interpretation is the same. And we are going to stick with standard error again just to help us remember that it comes from a sampling distribution, or more specifically that it's referring to a sample statistic. And our last bullet here, it's used for making inferences about a population. All right, number 11, how do we find the bias and the standard error for the sampling distribution for p hat? One way is to run a simulation, and you can do that in today's group activity. Second way is mathematically without running a simulation. So if the following conditions are met, and the first condition is the sample must be randomly selected from the population of interest, with or without replacement is okay. And if the sampling is without replacement, the population needs to be much larger than the sample size. At least 10 times bigger is a good rule of thumb. So we'll see a formula for that later. And this is our population size is capital N. It should be at least 10 times bigger than your sample size. So just a reminder, this is population size. And this is sample size. Okay, so if those two things are met, then we have the following. The bias of p hat is 0. This tells us the mean of our distribution is p. This is a big result here. It also tells us that our standard error, which we're going to abbreviate with SE, can be found with this formula or this calculation. And you should check your formula sheets to find this where it's listed. So in our standard error, you find by taking p times 1 minus p, dividing by your sample size, and then taking the square root. Okay, and last reminder here again, standard error is just the name of the standard deviation for sampling distribution. Okay, so in 12, in a real-world application, we usually only take one sample from a population and we calculate one p hat. Again, p hat is your sample proportion. Keep in mind the bias and precision are both measures of what would happen if you could repeat your survey many times. So 2, we won't know the value of p. In a real-world application, we won't know what the value of p is, and this again is your population proportion. You can't find that or know that without doing a census. Okay, so the question then is, how do you calculate the standard error? Well, you get a pretty good estimate of the standard error by using p hat in place of p. So remember from the previous page, the standard error was equal to square root of p times 1 minus p over n. And we're just substituting in p hat in place of p. And when we do that, we put an EST here to remind ourselves that this is an estimated standard error. So that's from here. That's the estimated standard error. So again, this is called your estimated standard error, and it is a useful approximation to the true standard error. So that means that the standard error that's estimated should be pretty close to the actual standard error. All right, so 13, an example. According to the Mars Company, packages of milk chocolate M&Ms contain 20% orange candies. Let's suppose we examine 100 random candies. What value should we expect our sample percentage of orange candies? All right, so what do we expect p hat to be? Well, if we know that 20% of the population is orange, then we should expect that our sample percent should be close to 20% as well. So 20%, give or take a little bit. We probably won't get exactly 20%, but we probably won't be too far off either. Okay, so calculate the standard error. We're not doing the estimated one. We're going to do the actual standard error because we have p, that's our 20%. So we're going to use the formula from the previous page. Our sample size is 100. So you may want to press pause, calculate this, and then press play when you're ready. You should get a standard error of 0.04. Okay, and then if we take our answers, what we can say is we expect 20% orange candies in our sample, give or take around 4%. So again, we know we're not going to necessarily get exactly 20%, but here's our typical distance from the center. So we should be around 20%, give or take about 4%. All right, so how small should the standard error be for a survey to be considered good? Well, the answer is small enough to be useful. So consider the following two examples. All right, first example, an election poll of 1,000 registered voters found that 49% favored the incumbent candidate. So we're going to calculate the estimated standard error, and it's estimated because this value here is from your survey or poll, so that's a p hat. And this is your sample size. That's how many people were polled. So our estimated standard error, so SE with that subscript of EST, is going to equal 0.49 times 1 minus 0.49 over 1,000. And again, press pause, try this out. You should get a standard error that's estimated at 0.0158. So again, keep in mind that we're doing this because we don't have p. And p, again, is your population proportion. All right, in our second example, we have an election poll of 1,000 registered voters, so N is 1,000 again. And this time I found that 59% favored the incumbent. So here's our p hat. So again, we're going to calculate the estimated standard error. All right, so SE, and since it's estimated, we're going to put EST on here. This is the square root of 0.59 times 1 minus 0.59 over 1,000. And again, press pause, try this on your own. You get an answer of about 0.0155. So notice that these are both very similar in size. Okay. But the question is, which one's more helpful? So in which case is the estimated standard error more helpful? Well, if we go back up to here, let's start there. What we'll find is that if we were thinking about what we would expect from our sample, we would expect around 49%, give or take a little bit. We might add a little bit of the standard error to that. And here, if we did the same thing, 0.59% plus or minus that estimated standard error, we're doing the same thing, but it turns out in this second one, that standard error, estimated standard error is big enough to identify a clear leader. So here, our estimated standard error is big enough to identify a clear leader. And it isn't so much that this is bigger than the one we got before. In fact, it's smaller. But paired up with this tells us we should expect something around 59%. And since that's greater than 50%, it appears as though the incumbent has a good chance to win. Up here, your standard error really isn't big enough to identify a clear leader. So your estimated standard error is not big enough in this case to identify a clear winner. Okay, so in the answer to the second question, I pressed pause to write this in for you. It says, in which case is the estimated standard error more helpful? Well, assuming there are two candidates, then the second estimated standard error is more helpful because it helps us better predict the outcome of the election. We're fairly certain that 59% will vote for the incumbent, give or take 1.6%, which gives us numbers both above 50%. So that's what allows us to, again, come to this conclusion, a little bit more confidence that the incumbent's going to win. Whereas in the first one, we expect 49% to vote for the incumbent, give or take about 1.6%, same as above. But that leaves us with the question as to whether or not that's going to amount to more or less than 50% of the population. So the way these two operate together, both your p-hat and your estimated standard error, really gets to the question of when is it big enough to be considered good? When is it useful?